make the trip to Bangalore. I did make the trip a number of years ago, which I enjoyed very much, and I hope to do so again at some point in the future after the pandemic is over. The story I'm going to tell you about today, about topologically ordered matter and why you should care, is a subject that spans across a number of fields of modern science. In condensed matter physics, I'm a condensed matter physicist by training. Topologically ordered matter is one of the primary themes of modern research, but also it occurs in quantum information theory. For people interested in quantum information and quantum computation, the topologically ordered matter is very closely related to quantum error correcting codes. It also occurs in high energy physics. In fact, many of the ideas of topologically ordered matter come from ideas of quantum gravity that grew out of the high energy field in the 1980s. But the real origins of these fields goes back really about 150 years earlier, and that's where I'm going to start this story. So up in Scotland in 1867, there were two very well-known physicists. The first one, I'm sure everyone knows, Lord Kelvin, William Thomson, and I'm sure I don't have to tell you all the wonderful things that Kelvin discovered. The other one is someone who is much less known, but also was a very good physicist, a guy by the name of Peter Tait. And Kelvin and Tait collaborated, they were very close friends, and they collaborated together on many topics throughout their lives. In 1867, they were actually interested in a phenomenon of fluid flow, which started them along this path. The phenomenon is one that was familiar to really everyone, not just scientists in the age. Is the idea of a smoke ring or a vortex ring. So let me just draw a smoke ring here on the board, or on the paper here. So here you just imagine a invisible ring in the middle of the air, and the fluid, the smoke or the air, circulates around that ring like this, and then the whole ring comes out of the plane of the board at you. Now, back in the 1860s in Scotland, people used to do this very strange thing called smoking tobacco. So everyone was, they don't do that anymore because it's bad for you. So everyone was certainly familiar with smoke rings because a talented smoker could produce a smoke ring from their mouth. I'm told smoking tobacco is something like vaping, but I'm not really sure. Anyway, so those were all jokes. The thing about giving lectures over the internet is you have no idea if anyone's laughing. So I'm going to assume no one laughs at any of my jokes because most of my jokes aren't that funny. Anyway, so Kelvin and Tait were interested in studying these smoke rings, and Tait managed to build a machine that produced smoke rings so that they could study them more carefully. It's actually quite easy to build these machines. If you haven't seen them on the web, you should look it up, smoke rings on the web. Anyway, Tait showed this machine to Kelvin, and Kelvin was immediately extremely impressed. Wow. And he had a number of simultaneous epiphanies. The first epiphany is something that we still teach in undergraduate physics and undergraduate fluid dynamics. And it sometimes goes by the name of the circulation theorem, Kelvin's circulation theorem. The content of this theorem can basically be summarized by or I guess a corollary of this theorem, is the statement that if it were not for friction in the air, if not for the fact that air has viscosity or dissipation, then this fluid flow configuration where the fluid flows around this central ring, and this fluid flow configuration would continue forever. It would just keep going around and around and around. The smoke ring would persist forever. It would be completely stable. Now that got Kelvin thinking, where can you find a fluid that has no dissipation whatsoever, that has no loss, no friction, no viscosity? Well, fluids that have no viscosity, no friction, no loss, they do exist. We call them superfluids. For example, if you cool helium down to very low temperatures, it will become a superfluid. And indeed, if you start a smoke ring, a fluid flow configuration like this one, flowing in superfluid helium, it really will continue essentially forever, or until it strikes the edge of the container, which usually happens first. But Kelvin didn't know about superfluid helium. In fact, helium hadn't even been discovered in 1867. So he didn't know about superfluids at all. But he thought he knew about a superfluid, a fluid with no dissipation, no friction, no viscosity. And this is a famous mistake in the literature, which I will remind you about. And the mistake was called ether. So what was ether? Well, ether was supposedly a perfect dissipationless, frictionless fluid that fills all of space. And the purpose of ether was to carry electromagnetic waves through the universe. And they knew that this ether stuff had to be very dissipationless because you can see waves, you can see light from stars very, very far away. So let me draw a star up here. And there's the light coming from the star to your eye like this, and you can see it from very, very far away. And if there's any dissipation in this ether fluid, you wouldn't be able to see the light. Now, why did they believe that it was ether that was carrying electromagnetic waves? Well, they believed this for very, very good reason. They knew a lot about waves, and they knew that when they saw a wave on the water, what they were actually seeing was water sloshing back and forth. And when they heard a wave of sound in the air, they really realized that it was the sound moving back and forth. And they knew that light was a wave, or it had light wave-like properties, but they never saw any anything moving back and forth. But they hypothesized that such material should exist, and they called it ether. Actually, the concept of ether goes back hundreds of years before Kelvin to the philosopher René Descartes, who thought it up, and he basically thought it up saying, I think, therefore it is, and he just created ether. And that was another joke in case you missed it about René Descartes. But it's true, the ether was invented by René Descartes, and by the mid-1800s, all the scientists in the world believed that ether was what carried electromagnetic waves. So anyway, on the one hand, Kelvin believed in this ether stuff, this perfect dissipation of this fluid. And secondly, he had his circulation theorem, which tells you that if you have a perfect dissipationless fluid, then this smoke flow configuration, this type of fluid flow configuration, would be completely stable and would last forever. So that got him thinking, well, what then is a smoke ring in the ether? And he came to a really remarkable conclusion. He concluded that a smoke ring, this fluid flow configuration in the ether, would be an atom, like maybe a hydrogen atom. Draw that black hydrogen atom like this, H. And you could have a more complicated fluid flow configuration, maybe like this, where you have two linked rings, invisible rings like this, and the fluid would flow around this ring like this, and the fluid would flow around this ring like this. And by the circulation theorem, this fluid flow configuration would be stable for all time. And this maybe would be a hydrogen molecule, H2, for example. And then you could have something even more complicated. Maybe, let's see if I can draw this without making a mistake. Do this, and then this. You have a fluid flow configuration that imagine this knot, known as this trefoil knot, and then the fluid flows around the knot this way, and then this way, and so forth and so on. And this might be a more complicated atom, like maybe lithium or something like that. Now, this idea of what atoms are made of, known as Kelvin's vortex theory of the atom, it sounds completely nuts to us right now, because of course we know what atoms are made of. They're made of protons, electrons, and neutrons. And we also know there's no such thing as the ether, having been destroyed by Einstein after relativity. But it sounded like a really good idea in the 1860s, and a lot of very serious scientists were impressed by it and thought this might actually be true. And the reason that they liked this this picture of the vortex theory of the atom was two issues that they didn't know how to answer otherwise. One is, why are the atoms discrete, and why are they immutable? They're discrete because there's only so many different distinct knots that you can draw. So this is the simplest knot. Maybe this is the next most simple knot. This is the next most simple knot. And they're immutable because of the circulation theorem. This knot will never turn into this knot without cutting a strand, which never happens by the circulation theorem. Anyway, so a lot of people took this seriously, although there's some people who criticized it right off, and one of the people who criticized it right off was Peter Tait. Tait said, well, it's a nice theory, but it doesn't predict anything about the atoms that you would want it to predict. You would want it to predict things like the masses of the atoms, or the electrical properties of the atoms, or the chemical properties of the atoms, and it didn't seem to predict any of those things. So Tait said, well, it's probably wrong. Nonetheless, for about 10 years, much of the scientific community was really enamored of this Kelvin's vortex theory of the atom, and spent a lot of time trying to think, is there some way you can derive chemistry out of this picture of knots in the ether. At the end of those 10 years, most of the people in the scientific community had more or less given up on the vortex theory of the atom for exactly the same reasons that Tait had mentioned in the first place, that it didn't seem to predict anything useful. But for some reason, Tait at that point changed his mind. And he thought, well, okay, it doesn't predict anything, but it's a very beautiful theory. And sometimes, there's truth in beauty. And so maybe what I need to do is study this theory a little more, and then I will understand things like the periodic table of the elements that I'd like to understand more. So he thought what he needed to do was build a periodic table of all possible knots. This is the simplest knot, this is the next simplest knot, this is the next most simple knot. And he felt that if he had a table of all the possible knots, he would know something more about the periodic table of the elements. So Peter Tait, who's rightfully viewed as the father of the modern branch of mathematics known as knot theory, the study of knots, Peter Tait became the father of knot theory, which is a very rich and beautiful branch of mathematics, and a very important branch of mathematics. But of course, this got him, despite everything he learned about knots in building his periodic table of the knots, which is known as the Tait table of the knots after him, he of course got no closer to learning anything about the periodic table of the elements, because of course this has nothing to do with atoms. So it gets to be around 1900. Peter Tait is a little bit older, and he writes some letters to his friend Lord Kelvin, talking about how depressed he is about the situation of his scientific research, that he spent an enormous amount of his effort over the course of 25 years or so building his table of the knots, and yet he is no closer to understanding anything at all about the periodic table of the elements. The following year, in 1901, his son, Freddie Tait, who was actually a champion golfer. If anyone's a real golf fanatic, they will know that the Freddie Tait Cup in golf is still awarded every single year. Peter Tait himself was actually a champion golfer as well, and also a champion rugby player. He represented the Scottish national team, among other things, on playing rugby. Both of them very athletic. But anyway, the son, Freddie Tait, the champion golfer, was killed very young in the Boer Wars in South Africa. And this put Peter Tait into a terrible, terrible depression, and from which he actually never recovered. And he died just a few months later, extremely sad over the loss of his son, but also being depressed about feeling like he wasted an enormous amount of his scientific career on this theory of knots, which really actually has nothing to do with the periodic table of the elements. Nonetheless, during his exploration of knots, he hit on what is really still the key issue in understanding knots, which I'll explain to you now, and then I'll also explain to you why it's important in physics. So let me explain to you what it is that Peter Tait understood. So let me draw two simple knots. Here's one knot, just sometimes called the unknot, just a simple loop like this. And then let me draw a second knot like this, a little bit more complicated. And the question is, are these two things equivalent, or are they inequivalent? In other words, can I take this picture and somehow untie it without using scissors, without cutting any of the strands, and turn it into this. If it can be turned into this, we say they're topologically equivalent. And if it can't be, we say they're topologically inequivalent. If they're topologically inequivalent, we would say that there are two entries on Tait's table of knots. They would correspond to two different elements, I guess, of his periodic table. If they can be deformed into each other without cutting, then they're really the same entry in the periodic table. Now, we're all pretty smart here, and we can tell, even without much work, that all you have to do is unfold this, move this strand over here and this strand under there, and then this picture on the right looks exactly like this picture on the left. And then, therefore, these two things, without cutting, can be turned into the same picture, so they are topologically equivalent. They look exactly the same entry in the periodic table. Seems like an easy question to answer, but in fact, when you get to more complicated knots, it rapidly becomes extremely difficult to tell if two knots are the same or if they're not the same, if they can be deformed into each other without scissors. So for example, this picture, the so-called trefoil knot, you can compare this trefoil knot to its mirror image. And it was only in the mid-1920s, I believe, about 20 years after Tait's death, that someone managed to prove that the trefoil knot is not equivalent to its mirror image. So that's leave that as a challenge to you. If you don't know how to do it, you can try to figure it out. Anyway, when the knots get more complicated, it gets even more difficult to tell if two knots can be deformed into each other or not. Anyway, what Peter Tait realized is trying to tell if knots can be deformed into each other without cutting is a hard mathematical problem, and you need some mathematical tool to help you. And the mathematical tool that he used, he never used this word actually, although it's pretty clear he understood this, is what we now call a knot invariant. So let me define what a knot invariant is. A knot invariant is a mapping from a knot or a picture of a knot as an input via some set of rules to some output. Okay, and the output can be a number, or it can be a polynomial, or it can be a color or something like that. It's not so important what the output is. The important thing is that the rules are cooked up in such a way that topologically equivalent knots have to give the same output. Let me repeat that. Topologically equivalent knots have to give the same output once they go in the set of rules. So, for example, if you have two really super complicated knots and you don't know if they can be deformed into each other or they can't be deformed into each other, you stick them into the set of rules. If you get two different outputs, then you know immediately that there's no way to deform one knot into the other knot without cutting and make them the same. They're necessarily two different entries on the periodic table of knots. So you can imagine why it is that having at your disposal knot invariant sets of rules with this property is going to be very useful in distinguishing knots from each other and in building this periodic table of the knots. So to show you how these knot invariants work, I'm going to define a particularly simple and particularly useful knot invariant, sometimes called the Kauffman bracket, Kauffman invariant or Kauffman bracket invariant, And the Kauffman bracket invariant is named after its inventor, who is actually von Jones. Jones, so that was actually a joke. It's not named after its inventor. Its inventor was von Jones, but it's named after Kauffman. And still, I can't tell if anyone's laughing. So von Jones is an extremely famous mathematician who just passed away last month, actually, at a rather young age. He's a Fields medalist. He won his Fields medal for work on the theory of knots. Kauffman, after whom this is named, is another very important mathematician. He's still alive and doing very well. The reason this is named after Kauffman is because what Kauffman managed to do is he took some of the things that von Jones was doing, which seemed extremely complicated, and simplified it so much that I can explain it to you in about 2 minutes, which is what I'm going to do. So for my taste, this is at least as important as what Jones was doing at the time. But anyway, so that he gets his name attached to it, although he did not win a Fields Medal. So so in order to define the Kauffman invariant, we have to first pick a number, and we'll call it A. A stands for a number. And right now we'll leave it just arbitrary variable, although we will give it an actual value later. For now it can just be a variable. And then there's only two simple rules of the Kauffman invariant. The first rule is that a loop of string with nothing going through the loop of string, nothing over, nothing under, just a simple loop of string like this, can be replaced by the following combination: minus a squared minus a to the minus 2, okay? And this combination occurs so often, we give it its own name. We call it D, okay? So that's the first rule. It's a very simple rule. The second rule is a little bit more complicated. If you have a picture of a knot where two strings cross over each other like this, we can then replace that picture with a sum of two pictures. So the first picture has the two strings going vertical, and the second picture has the two strings going horizontal. And we also give coefficients out front of A and A inverse, okay? So what am I doing here? What I'm doing here is I'm doing some sort of algebra with pictures. I'm taking a picture and I'm rewriting it as a sum of two pictures, and these pictures get coefficients out front. Now, if this is not clear, I'm going to do an example of it to make it clear in a moment, or hopefully make it a little bit more clear in a moment. Now, these are the only two rules we need, but I'm going to add a third rule, and the third rule looks exactly like the second rule, except I'm rotating all the pictures by 90 degrees. And so it's really just the same rule, looking at the pictures sideways. So you can see that this is just this rotated by 90 degrees, this is this rotated by 90 degrees, this is this rotated by 90 degrees. And the reason I'm drawing this rule twice is because it's a lot easier to draw the rule twice than it is to ask you to rotate your head in a few minutes, okay? So what I'm going to do now is I'm going to use these rules to calculate the Kauffman invariant of a very simple knot. So let's choose this knot again. Okay, there. And what we do is we focus in on this crossing here, in that little blue loop up there. And you see that crossing looks exactly like this crossing up here. Okay, so I can replace that crossing. Oops, make it black. Replace that crossing with A times vertical plus A inverse times horizontal, just like this rule tells us to. And then the rest of the picture gets filled in exactly as it is over here on the left. So the rest of the picture looks like this. It gets closed up on the top. And then there's one crossing on the bottom. Okay. So are there any questions about what I just did? Because if you understand this, you'll understand pretty much everything else that I've done. Oops, there's something in the chat. I see there's questions and something in the chat. We should have a smile in addition to raise hand. Okay, yes. I will take that as someone laughing at my joke. Second question, how can one verify that this is the case for each and every knot without either A, studying all possible knots, or B, knowing something very general about knots? I'm not sure I understand the question there. So either add more to that question from Rajarshi so that I can understand what the question is, or I will answer it in the discussion later. Okay, anyway, so if everyone understands this step, we can then in these pictures, we now have a sum of two pictures, and in these two pictures, we have crossings here, and these crossings look exactly like this crossing here. So this is the statement is this is about something very, this is so I'm defining. Okay, let me just repeat, see if I can answer this question. I'm defining this set of rules. If you evaluate this set of rules, you will get an output. And so I'm going to do this example and show you how we get an output from applying these rules, and then we'll go on. Let me see if I can answer this question more in a moment. Okay, so now we have these two pictures here, and I want to apply this rule to get rid of these crossings. Okay, so let me do this really quick. So this A comes down here, so I'll put A out here. I'm going to open up brackets. And then I'm going to have apply the second rule, A times horizontal plus A inverse times vertical, and then fill in the rest of the picture exactly as it is up here. So that means everything gets closed up on the bottom, and everything gets closed up like this on the top. And then I'll move this guy down here. So there's an A inverse, and I get A times horizontal plus A inverse times vertical. And then I fill everything in, oops, exactly as it is over here. So it's a loop on top, like this. It's gonna close up like this, it's close up like this. Okay, all right. So at this point, all the pictures I have left are just simple loops. If you can see that. So each of these loops, there's no crossings left. Each of these loops is just replaced by the constant d. Okay. So let's just do that really quick. So here I have a times a, 2d's is d squared. So the first term is a squared d squared. In the second term, a cancels a inverse. There's one loop, so I get plus d. The third term, a cancels a inverse. I have 3 loops, so I get d cubed. And in the third term, I have a to the minus 2 and 2 loops. It's a to the minus 2. 2 loops is d squared. The final thing I have to do is I want to, let me just copy this here. We're going to need that identity. Copy. So I'll write it out down here again. Paste. I'm going to use that identity. So I can put together this a2 and this a to the minus 2 and get minus d. So that means this term and this term come together to give me minus d cubed. This minus d cubed cancels this d cubed. And at the end of the whole calculation, I just get d out in the end. Okay. So yay. Why is the yay? Why does that get yay? The reason that gets yay is the following. At the beginning of the day, I had this knot that looked a little bit complicated. But secretly, we knew that this knot is actually just the same as a single loop, right? We could just unfold it and make a single loop. Now, a single loop, the Kauffman invariant of a single loop is worth d. So this thing is supposed to give us d. I tried to make the knot look more complicated by folding it over, making it look a little bit more complicated. And at the end of the day, it still gives me d. I could have folded over the knot 100 times and made it look super, super complicated. And at the end of the day, I still would have gotten the same result. I still would have gotten d. Okay. So that's how knot invariants work. So you can sort of imagine how it is that this kind of tool is going to be very useful for helping you build your periodic table of knots. Now, I guess the question that's written in the chat is how do I know? Basically, I'm going to calculate define for a loop. So okay. So I think this is both 2 questions that I wrote down this set of rules. Okay. And the claim was that if you apply this, so in this set of rules, this loop gets the value minus a squared minus a minus 2, which we define to be the number d. Okay. Now I claim that if you evaluate this set of rules for any knot, you will get an output which is independent of how you present the knot, independent of how you fold it over, and may try to make it look complicated, it will come out exactly the same for any two knots which are topologically equivalent. In other words, if I can deform two knots into each other without cutting, the claim is once you evaluate the knots using these sets of rules, you will get the same output for any two knots that can be deformed into each other without cutting. Okay. Now I didn't prove that. It's not too hard to prove that this set of rules will give you a knot invariant. That it will give you a result which comes out exactly the same without cutting. And the way you prove it is roughly the way you prove it is you start checking that if you do something like this, you can change, if you change a knot from, that looks like this, has two strings like this, and you turn it to something like this, you'll get the same result. That's basically what we did here. We pulled two strings over each other, just like this. And then you also have to check things like, if I have a picture like this, I can deform that into a picture like this and still get the same result. So it's not too hard to prove that these rules give you a knot invariant, give you something that only depends on the topology of the knot and not on how much you've tried to munch it up and make it look more complicated, but I haven't done that, okay? So I hope that this is that clear now, I hope? Yeah, okay. So this, having this knot invariant at your disposal is something that's this is not a knot invariant that Peter Tait had at his disposal, because this wasn't invented until the 1980s. But he had some other knot invariants which were useful to him. So you can imagine that this might be a useful thing to have if you're trying to distinguish knots from each other. If you put two knots in, you get different outputs. The knots can't be deformed into each other. Now, if you think about it a little bit harder, you'll start to realize that actually it's maybe not as useful as I suggested it is. Why? Well, this particular knot we started with here, it had two crossings, and we ended up with 4 diagrams. If it had 3 crossings, we would have gotten 8 diagrams. If we had 4 crossings, we would have got 16 diagrams, and so forth and so on. The number of diagrams we get, number of diagrams is 2 to the number of crossings. And unfortunately, things that grow exponentially, well, we know a lot about exponentials. Whenever something grows exponentially, it always ends in sadness in one way or the other. And the problem here is that it's really easy to draw a picture of a knot which has 100 crossings. And yet the number 2 to the 100th power is such an enormous number that if you put these rules on the world's biggest computer, and you ask the world's biggest computer to start computing, it would never, in 1,000 years, it would still never be able to spit out an answer, because it would have to evaluate the Kauffman invariant for 2 to the 100th diagrams, and that number 2 to the 100th is just way too big. So this Kauffman invariant seems like it's not going to be all that useful for really complicated knots. And we'll come back to that in a while. Okay, so now after that long discussion of knot theory, you're probably wondering, well, what does this have to do with physics, and which I'm about to explain to you. So let me introduce a concept which sounds like it's completely different, but in fact is almost exactly the same. It's the idea of a topological quantum field theory. And actually, I guess I should, well, let me give a sort of this is topological quantum field theory is almost equivalent to topologically ordered matter, which is part of my title, topologically ordered matter, in the following way. Topologically ordered matter is the matter you have in your laboratory, which can be described mathematically by a topological quantum field theory. So topological quantum field theory is a mathematical description of something that we call topologically ordered matter. Okay, that's not, seems like a rather self-referential definition there. So let me try to give it define them both now. So topological quantum field theory is a QFT, or any quantum system. Let's say any quantum system. Any quantum system where amplitudes depend on only topology, not geometry. Okay, that's an important statement. So I've written it out. Topological quantum field theory is a quantum system where amplitudes depend only on topology, not on geometry. It probably sounds confusing right now, so let me see if I can explain it a little bit more. So I should specify here that every diagram I'm going to draw from here on, I'm thinking about the following situation. We're imagining a two-dimensional system. So here's a two-dimensional system. We'll think of it as disk, like this. And I'm going to draw time going vertically. Time goes vertical, like this. Okay, that's not vertical. It's kind of slanted. That's not vertical either. I'm not doing very well. There, that's vertical. Or vaguely vertical. Time going vertical. Time goes up. Time is money. Money goes up. Okay, it's going up. Time goes up, and space is horizontal. So let me draw an experiment which asks us to measure some amplitude, or probability amplitude. So let's imagine that this this physical system is in its ground state, and let's imagine the ground state is gapped also. So there's some ground state, and it's just sitting in its ground state and doing nothing. It's a very boring system, but we always have the option of adding some energy to the system to make it do something interesting. So let's add energy, say a photon or something like that, and we can create from the vacuum a particle-antiparticle pair from the vacuum at some time. If you're a condensed matter person, you would call it a particle-hole pair. And if you're a high energy person, you would call it a particle-antiparticle pair. And then maybe at some later time, we'll do that again. We'll add some more energy here, and we'll make another particle-antiparticle pair. And then maybe we'll take one particle around the other particle like this, and then we bring them back together at some later times here. And maybe these come back together here at some later time. And then we want to measure what happens when we bring them back together. Now, there's several things that can happen. One thing that can happen is that they can emit their energy back in, the way that it came in. It can re-emit a photon or something like that, or a phonon, get rid of the energy, and return the system to the same ground state that it started with. So you get back the original ground state that you started with. But another thing that can happen is that it can form some sort of bound state, like this, that refuses to re-annihilate back to the vacuum. Both of those things are possible. So you can either get annihilation, or you can get bound state formation. Now, there's some probability for each of these things happening, and it should not bother us that that we have a probabilistic outcome, because we know in quantum mechanics that lots of measurements give us a probabilistic outcome. That you have some probability amplitude of getting one result, and some probability amplitude of getting some other result. And depending on, and you square the probability amplitude to get an actual probability, and you do the experiment many, many times to make a measurement of that probability. Okay, so what do I mean by the statement that the amplitudes depend only on topology, not on geometry? What I mean by this statement is I could change the experiment. Let's change the experiment a little bit, and let's deform this path like that. The statement is that the probability of the outcomes is unchanged, because I didn't change the topology of the picture. I only changed the geometry. The geometry has changed. I changed the shape of that curve, but I didn't change the topology, that it's two rings that have been knotted. I could make another change too. For example, I could you know, make this, deform this like this, make it like that, that. And I still haven't changed the topology of the picture, but I've changed the geometry. And the statement is that I will still get the same amplitudes of the outcome at the end of the day. Now, this should be a little bit surprising to us, that that you have such systems where only topology matters, that it doesn't matter how I deform these pictures geometrically, that only the topology matters in the outcome amplitude, because we're used to the idea that details matter when you do your quantum mechanical calculations, that things matter like how close the particles got to each other, and things matter like how fast they were moving, how long they lived before they tried to reannihilate. And I'm telling you that in a topological quantum field theory, or in topologically ordered matter, these things don't matter at all. The only thing that matters is the topology of the picture, the world line picture that has been created before the particles come back together and they reannihilate. So what's kind of interesting here is that the outcomes, the probabilities, outcomes, or the probability amplitudes, if you want, are obviously not invariants. Why? Because they are a mapping from an input, which is a picture of a knot here, here's a picture of a knot, to an output, which is some probability amplitudes, which depends only on the topology of the knot and doesn't depend on the detailed geometry. You can make this look a lot more complicated by folding it over and making it look at, you know, as long as you don't use scissors, you will still get the same outcome, the same probability amplitude outcome. Therefore, the probability amplitudes are themselves not invariants. And this connection between topological quantum field theories and not invariants was made very famously by Ed Witten. Ed Witten is one of the world's most famous string theorists. Witten was awarded the Fields Medal along with Von Jones for his work in the theory of knots. And, you know, okay, so this, you know, this connection, this rather beautiful paper that Witten wrote in 1989 that opened up what people now call quantum, the field of quantum topology, it makes a connection between quantum field theories and knots. And one of the things that, many things were done in this one paper by Witten, but one of the things that he did, which was particularly interesting, is he made a mapping between some known topological quantum field theories. So they were, I'll call it TQFT for topological quantum field theories. There were known gauge theories known as Chern-Simons theories, SU. So Chern-Simons theory is a gauge theory, which means we have to have a gauge group. We'll choose SU2 as our gauge group. And then it needs a coupling constant K, which must be an integer. And these were known topological quantum field theories. And what he showed was, if you want to know, if you have this topological quantum field theory, the Chern-Simons type SU2 level K, and you want to know the probability of all the particles reannihilating, probability of annihilation, all you need to calculate is the Kauffman invariant of the knot squared. So the Kauffman invariant gives you the probability up to some normalization, which I'm not giving you, but up to that normalization, all you have to do is calculate the Kauffman invariant and square it. The one more thing that you have to do is, if you remember where I defined the Kauffman invariant, we had to define a number here. So the number you have to insert in the Kauffman invariant depends on this integer K. It's A equals, I guess, oops, come back, I e to the I pi over 2K plus 2. So if you're looking at this particular type of topological quantum field theory and you want to know with these particle types, you try to bring them back together and reannihilate, you just take this knot, calculate its Kauffman invariant using this value of A, square it, and you get the probability of all the particles reannihilating up to a normalization, which I'm not going to mention just because it's a detail. Okay, so what is perhaps more surprising than all of this is that these topological quantum field theories are not just a figment of Ed Witten's overactive mathematical imagination, but in fact, we believe that we have seen many of these things in the laboratory, that topologically ordered matter really does exist in nature in several different guises. Now, I'm only going to discuss the topological quantum field theories of type SU2 level K, SU2 sub K here, with K being an integer, but there are a few proposals for things like SU3 that are known out there, but not many. So let me make a list. SU2 level 1, these course SU2 level 1 corresponds to a U1 theory for those people who are familiar with it. That's an abelian anion theory for those who are familiar with it. And most of fractional quantum Hall effect, fits in this, fits here. Rather interestingly, in the early days of fractional quantum Hall effect, fractional quantum Hall effect is about 40 years old now. And in the very early days, people proposed that the particles in, there's a question, and the question is, how can one distinguish between two different quantum processes with the same topology as the probability amplitudes of them are the same? How can one distinguish between two different quantum processes with the same topology? For making the measurement here, you can't distinguish. If you have two quantum processes with the same topology, and you make these measurements at the end of the day, you get the same probability amplitude as a result, and so you cannot distinguish them, even though they may geometrically look different. Right, so anyway, fractional quantum Hall effect, it was discovered 40 years ago. I'll say a couple more words about fractional quantum Hall effect at the end of the talk if we have time. Oh, I'm running out of time rather rapidly, so maybe I won't. But the first demonstration that the particles in fractional quantum Hall effect have interesting properties when you braid them around each other, that it really is topologically ordered matter. This was done in two very beautiful experiments done just this year. So for essentially 40 years or 35 years at least after this was first proposed theoretically. SU2 level 2 is more interesting, and there is maybe the most prominent of the SU2 level 2 phases of matter that we're familiar with is one particular fractional quantum Hall state, We'll say more about fractional quantum Hall effect later. Helium-3A film. So helium-3, you recall, is the helium that is missing one neutron, so it's a fermion. If you cool it down to very low temperatures, it becomes a superfluid, and one of the phases of that, if you make it a film, so it's a two-dimensional system, so everything I'm talking about is two-dimensional plus time, it becomes SU2 level 2. There's a large number of engineered things. Anytime you hear people say that they're trying to engineer Majoranas, these are all essentially SU2 level 2 class. There's a number of materials that people are excited about now. Uranium tellurium-2 is now a new one people are excited about. Iron tellurium 0.55, selenium 0.45. Another compound people are excited about that they believe is in this class. I used to list strontium rutheniate in this for a very long time. People thought this was in this class, but now the newest experimental evidence seems to say it's not. There's SU2 level 3, and the only thing known there is one more quantum Hall state, nu equals 12/5 fractional quantum Hall effect is believed to be in this class. And there's some others that I haven't listed as well. So I'm running out of time. So let me skip a little bit and just, okay, let me just say a couple words about one of the reasons why, and I may hang over a little bit into the hour, over the hour here. So one of the interesting things about topologically ordered matter is the following statement. That if you have your two-dimensional system, and in most two-dimensional systems, or most any dimensional systems, if I start with the ground state and I say I want to add to the ground state some number of particles and antiparticles. So I'll put a particle here, an antiparticle here, a particle here, an antiparticle here. Usually if I tell you that information, I have told you the wave function of the system. But that is not so in the case of topologically ordered matter. Let me make a copy of this. I can make two linearly independent wave functions, which actually let me make 4 copies of this, might be useful. Paste there, okay. I can make 2 different linear independent wave functions. Let's call them 1 and 2, like this, which look exactly the same in the sense, to any local measurement, in the sense that I say, okay, start with the ground state and I add particle, particle, hole, and hole, particle, particle, hole, and hole, and yet they're different. Why is that? Well, in topologically ordered matter, you have to think about the topology, the space-time topology of what you did. And there's 2 ways that I could have created these. I could have created them like this, or I could have created them like this. And these 2 are topologically different. And so they can be different wave functions. And to prove to you that they're different, I am going to take overlaps of them and show you that, that they give you different results. I'll take different overlaps between them and overlaps between themselves. So to do that, I need to construct the bras to go with the kets. So the bras are just the time reversal of the kets, like this, like this. And in order to take an inner product between a bra and a ket, what you have to do is just squeeze these 2 pictures together. Just you know, bring the bra down to meet the ket. So for example, if I want to calculate 1, 1 like this, here's the physical system in the middle, and then it looks like this on top and it looks like this on the bottom, and so that's 2 loops, and so that's d squared. Okay, I could do the same thing with 2, 2. 2, 2 will give me hole, particle, hole. So like this on top and like this on the bottom. That is also 2 loops, and so that is d squared. But if I take 1 on the top and 2 on the bottom, so 1 on the top looks like this, but 2 on the bottom looks like this, that is actually topologically 1 loop, and that's d. So this tells me that 1, 1 is d squared, 2 and 2 is d squared, but 1 and 2 is d. Tells me that 1 and 2 are linearly independent. Okay. Now, this finally brings me back to the first statement that I made in the talk, which is why, you know, the first question I posed, which is why should you care? And the reason you should care is because this 2-state system, the fact that I have 2 linearly independent wave functions, makes a really good qubit. And you can manipulate this qubit. For example, you could make some more complicated braid like this. This one goes behind, maybe this one goes like that. And by making that complicated thing, I would get 1 braid 1, and I could evaluate this by evaluating the Kauffman invariant. Now,
Steve,
you know, the idea of using this for quantum computation is known as topological quantum computation. Topological quantum computation. I'll finish in about 2 minutes. Computation. Hello?
Steve, there is a question in the chat.
There's a question. While taking inner products, why don't we consider topologies where loops are linked? Well, we can. So what I did here was I just took these pictures here and I squeezed them together. You know, the physical state up here and the physical state down here are the same. They have particles at the same places and holes at the same places. I have to match up a particle with a particle and a hole with a hole. And so this one has to match up here. This one has to match up here. And these 2 have to match up like this. So in this picture, I can have a picture where the things are linked, but I had to put something more complicated in between. So I hope that clarifies what's going on there. Ask again at the end if I didn't answer properly. So the idea of topological quantum computation is credited to two very smart people. One is Alexei Kitaev, maybe one of the smartest people around in the physics community these days. Many of the greatest ideas come from here. And the other is Michael Friedman, who's also a Fields medalist for his work on the Poincare conjecture in the 1980s. So their idea basically looks like this. You start with your two-dimensional system, and each time I did this, I created two pairs of particles. I had one qubit in some particular state. So let me make a whole bunch of qubits. Here I made 4 qubits. Each one of those made a two-state system. If I want to do some computation, I then do some really complicated braid. And okay, I'm trying to draw very quickly something that looks kind of like a braid. Okay, this one goes around like this. Okay, all right, complicated braid. That's not a very good drawing. But then at the end of the day, I try to bring them back together. And then I make a measurement of the outcome. How many of these guys reannihilate to 0 and how many of them form bound states? That's the measurement at the end of the day. Now, so a couple of things that I should convince you before I'll go over about 3 minutes before ending. The first thing I should convince you is that you can do quantum computation this way. Let me just ask you to think back to the beginning of the talk where I defined the Kauffman invariant and remind you that the complexity, well, it's way back up here, the complexity of calculating the Kauffman invariant of a really complicated knot is 2 to the number of crossings. But if I really needed to know the Kauffman invariant of a really complicated knot, I could, if I had this topological quantum field theory in my laboratory, I could just form the knot by dragging the particles around each other, and then the probability that they all reannihilate is the Kauffman invariant. So I could just measure whether they all annihilate, repeat the experiment many, many times to get an extremely good estimate of the Kauffman invariant. So it gives me a way to calculate Kauffman invariants of knots, which is something that modern, the conventional computers cannot do. So this sort of topological computer that uses topologically ordered matter can do certain calculations that other computers basically cannot do, that are exponentially hard for regular computers. And it turns out that it's not too much harder to convince yourself that you can do any quantum computation using this approach. Now, the second reason why people are interested in this is not just that you can do quantum computation, but it's actually a fairly good idea to try to do it this way. And the reason is because most quantum computers have a serious problem due to coupling to the environment or noise in the environment. And you have to ask whether, I see that there's another question, but oh no, it's the same question. No, okay, it's the same question. Let me answer it in a minute. Let me finish what I'm saying. So the most quantum computers, the problem is noise in the environment. That noise in the environment can ruin your quantum computation, and you have to go to great lengths to try to protect your computation from errors. Now let's think about what happens if we add noise here, noise to the environment. What happens? Well, what happens is instead of making a nice smooth path, that particle might make a wiggly path. However, as long as you don't change the topology of the knot, you didn't do anything wrong. That the computation is inherently immune from small amounts of noise in the environment because it only detects the topology of the braid. It doesn't detect the detailed geometry. So that's this sort of inherent error protection is why people are interested in this this approach for quantum computation. I was going to go on and say a couple words about fractional quantum Hall effect, which is the case where we know the most about, or most convinced that what we have is topologically ordered matter, and we've done the most experiments on it. But I see that I've run over, so maybe I'll stop there and take questions. And if someone wants to ask me about fractional quantum Hall effect, that's okay later. So let me go back and read the question. Is it because we could Kauffman split them to the ones you showed? No. Okay. So the question is, when taking inner products, why don't we consider topologies where the loops are linked? So let me try to explain a little bit more what I've done here. So here I have some physical system with some particles and some holes in it. Let me put a bunch of them like that. And I'm not drawing an entire knot here. I'm drawing half of a knot. So this is a ket. A ket corresponds to half a knot. So it has the space-time history of half a knot. And these can be connected. Oops, what just happened there? I connected a particle to a particle. It has to be connecting a particle to a hole. So this one has to connect like this to the hole. This one goes like this. It goes under that, maybe behind that, and up to here. Okay, so this is half of a knot. Okay, and it can be knotted or whatever you like. And then I can have a bra. The bra, I want to have that thing start at the same point. So the particles and the holes are at the same 6 points here, and I can put any complicated knot over here, linked or not linked. And then if I want to know what bra ket is, I just connect up these two pictures in order to make a single knot. So I can do that by copy here, copy, paste, like this. Okay, there's the top, and I'm going to copy and paste this guy. Oops, it's not doing it. Okay, I'm not able to do, oh, there we go. Copy, paste, paste here. Okay, I'm trying to make it a little smaller so it fits exactly. I didn't size it correctly. I just fit these guys together like that to make a single knot. And now I have a knot equals, if they had fit together perfectly, equals knot. And then I can evaluate the bra and the ket by taking Kauffman invariant equals Kauffman of knot. Is that clear? Other questions? So I think I've ended the talk unless people have questions or comments or want to.
Thank you, Steve, for the nice talk. Questions, it would be nice if you want to raise your hand one by one, and then I can ask you.
Okay,
so Anubhav Srivastava, can you unmute yourself and ask the question?
Okay, so am I audible?
Yeah, yep.
Yes.
Yeah, okay. So this topological quantum computation, is it possible only in non-abelian statistics or in abelian as well?
It's correct. It's only if you, okay, so there are different things that people want to use they go by the name of topological quantum computation. If you want to have a set of particles that where you can do all quantum computations just by braiding them around each other, then you need non-abelian statistics for sure. It's nice if you have non-abelian statistics, even if you don't even want to be able to do all or are willing to settle for not even being able to do all possible computations. But you just want a quantum memory. But abelian statistics are actually good enough if you want a quantum memory, although maybe more complicated. For example, the toric code is an abelian case, and it's actually the premier example of a really good quantum memory. And it also goes by the name of the surface code, and it is abelian, but you can't do computations with it, at least not by just dragging the particles around each other. Other questions?
Yeah, other questions? There is one by Srikant Pai. Srikant, would you unmute yourself and ask the question?
Yeah. Hello. Hi, am I audible?
Yes.
Yeah. Hey. So I just want to know, how do we deduce the rule of the inner product from the rules of quantum mechanics? Why is it that smashing these pictures together gives us the inner product?
Yeah. So this is not obvious at all. I agree with that. This is basically part of how topological quantum field theory, topological quantum field theories operate. So I guess once I mean, you could say this is an axiom of topological quantum field theory in some sense. But let me try to justify it in a slightly different way. So if we know we have a theory where the outcome of a computation is completely topological. I mean, the outcome, the probability amplitude, the outcome of a measurement, it only depends on the topology of what went in. Now, most theories don't have this property. This is very unique to topologically ordered matter. But let's start with that as an assumption that the outcome is going to be dependent only on the topology of the input. Then we can ask, well, what happens if you take this picture and you slice it in the middle? Okay, you slice it in the middle. You will necessarily have a, you can think of, you can always relate things back to the vacuum. So propagating forward to the vacuum, and then bras propagate forward in time, and kets propagate backwards in time in some sense, because you've complex conjugated the time reversal or something like that. So you can sort of think about the going, yeah, let me put it this way. When you slice this in the middle, you have a picture that knows about everything that happened at an earlier time. That goes into the bra, and then everything that happens at a later time has to go into the ket. So when you squeeze them together, you make a closed knot, and everything on the earlier side is on one half, everything on the later side is on the other half, and then you put them together to make a knot, and then the result has to depend only on the topology of the knot that you form. So in some ways, it's the only possible result once you know that the outcome of your measurements have to be dependent only on topology. Okay, but it certainly isn't obvious, and it isn't true for most systems. It's very special to topological systems. Is that potentially a good answer, satisfactory answer?
Right, interesting. So essentially, it's like it's like a rule, basically, right? Like
it's a rule. Yeah, it's a rule. But I guess what I was saying is that once you have the statement that the outcome, once you have this definition that the amplitudes of the outcome only depend on the topology, it's the only rule you could have given.
Oh,
okay. So it's necessarily follows.
Vijay Shenoy.
Thank you, Steve, for a wonderful talk.
Vijay, good to see you.
Good to see you. So the question that I had is, what is the answer to Tait's question, in the sense that, see, suppose I take the Kauffman invariant, I suppose I can write it as some kind of function, right, of A. So what are all the allowed functions for such invariants? Is that the way you pose the question? And if that's the way you pose the question, what's the answer? Okay.
So let me pose the question in a slightly different way. One question is, what values of A are allowed in the Kauffman invariant? Okay, so physically, not all of them are allowed. There's for a physical system, one thing that I didn't have time to mention, although often I do, is that this A has to be has to have a unit magnitude. It's not too hard to show, actually. For a physical system, whereas as a non-invariant, it can be any number at all. Or, it can even have, it doesn't even have to live in a number field. It can be some complicated thing. But for a physical system, it has to be a complex number of magnitude 1. Then you might ask, well, can you come up with not invariants which have similar types of rules, but are different rules? That is Kauffman sort of the simplest case of more complicated not invariants? And the answer is yes. There are more complicated sets of rules. So, for example, there's a not polynomial, not invariant, known as the Humfly polynomial. So Humfly is an abbreviation of the 6 people who invented it at the same time in several different papers. I probably don't remember. So Y is for Yetter, L is for licorice, O is Aknianu, I apologize to H, M, and F for not remembering who they are. But and this is a generalization of Kauffman, which corresponds to SUN level K. But you can go, but there are other things you can do as well. It doesn't have to be SUN. You can have, you know, other Lie groups, SP, and they have some set of rules, level K. You can have cosets, SUN, K, mod, SU, you know, M, P, so forth, and they have other rules, and so forth and so on. So there's quite a few different possible sets of rules, and I guess what's equivalent to this statement is asking, you know, can you make a periodic table of all possible, of all topologically ordered matter, top ordered matter, or TQFTs, of all TQFTs. And with, so this is a project that a lot of the community has, you know, a lot of the people in the community have worked on over the last 2 decades or so, adding very small restrictions. You know, these periodic tables have been built, but, you know, there's an infinite number of possible TQFTs, but many of them, at least the simple ones, are all classified and categorized at this point. And, you know, they get, it turns out that if you restrict yourself to TQFTs that don't have fermions in them, it actually becomes a lot simpler. So those were classified first, sometimes known as modular tensor categories, MTCs, modular tensor. And the statement I made that it doesn't have fermions in it is not exactly a precise definition of what a modular tensor category is, but functionally it actually is a pretty good definition. So periodic tables of these have been made, and the way that you build these periodic tables is you say, okay, let's think about in a particular TQFT what kind of particle types exist. You know, so you might have in a simple TQFT where there's, you know, the so-called the trivial particle type, the vacuum, which you call the identity, and then there's maybe one other particle type. Let's call, I don't know, call it P or something like that. How many topological quantum field theories can you write which only has the vacuum and the one non-trivial particle type? And it turns out that there's exactly 4, and I think that's probably right. If you exclude fermions, if you add fermions, you might have then 8 or something like that. I'm not sure what happens. But then you can say, okay, let's imagine a topological quantum field theory that has one particle that has, you know, the vacuum, and then 2 particle types, P and Q. Can you write down all the topological quantum field theories that that satisfy that? And then you can write down, you know, there's some number, some finite number. I don't know, maybe there's 15 or 16 or some number like that, and you can write them all out. And this program has been done for modular tensor categories up to about 5 or 6 particles where people start losing steam. And many of the things that you find are, you know, simple, end up being, you know, simple things like SU2 level K or SUN level P or something like that. And they're things that are known, but then you run into a couple stray ones that you might not have thought of. So, which are complicated cosets or something like that. So I'm not sure, does this answer your question at all?
No, you gave a broader answer. I was just wondering whether the specific question that Tait was after for the knots has said.
Oh,
yeah.
Oh, so, all right. So Tait's table, I mean, people have written down, you know, tables of knots up to, I don't know how many crossings, 16 crossings. I mean, the tables start getting exponentially big and complicated. Tait wrote down, actually Tait was way ahead of his time. He had some conjectures about knot theories that weren't proven until the 1990s, that he got right way back in the 1800s. his table of the knots, I think he went up to 9 crossings or something like that. And he only had 2 or 3 errors in his whole table, of which I think the last one was found in the 1970s, actually. Someone discovered there was an error. He had written down 2 knots that he said were different that turned out to be the same. And it was actually a non-professional mathematician, an amateur mathematician, who just liked playing with string, who got a copy of Tait's table of the knots, a guy named Perko, P-E-R-K-O, who just liked playing with string, and just made copies of all the knots on Tait's table. And he found 2 of them listed with some number of crossings, and he found that he could deform one of them into the other. And he said, aha, there's a mistake on the Tait table. And so now they're called the Perko pair of knots after him.
Okay.
So,
thanks a lot, Steve. Thank you very much.
You're welcome. Okay, good.
There are a couple of more questions. Anubhav first, and then Rajoshi.
Okay. Yeah, one more question I had. So in 2 dimensions, we have braid groups, right? So the braid group statistics are there. So when you represent knots in 2 dimensions, so those the condition, the Kauffman condition, is this become equivalent to those braid group conditions, or they're different?
It's different, actually. So it's true that you can take any knot, and it's known as combing a knot into a braid. So you can take some a braid is the lines are directed, like the lines always have to go up. They can cross over and under their neighbors like this, but they can only go up. So that makes a braid. But you can take any knot, and you take a braid from bottom to top. Okay, I don't have to draw it like this. So, and then connect up the top to the bottom in some standardized way like this, always like that. And you can take any knot and turn it into a combed braid where you basically close the top to the bottom of a braid and get out whatever knot you want. So that's certainly known. But the Kauffman rule, the braid group is more general, that the braid group tells you everything you need to know about knots in some ways. I mean, the braid group, it seems simple, but it's quite complicated. It's an infinitely big group. Whereas the Kauffman invariant is not a unique invariant. You can write many different knot invariants, as Kauffman invariant, a Hahn-Plahm invariant, or lots of other things. So they're related, but they're not the same.
Okay, sure. Thank you.
Yep. One more, Rajarshi.
Rajeshi.
Yeah, so about the rules, they depict or represent a way like I can transform a knot physically and I can get back another knot, and the rules represent mathematically how that these transformations are equal, like these
That's
two
right.
knots are equal. Yeah. So the rules are very mathematical.
Yeah. Hello?
Hello, Rajeshi.
Sorry, accidentally someone muted me. Okay, yeah. So the rules are very mathematical, whereas the transformations that I am doing is very physical. So I'm not seeing it correspondence to the physical transformation to these rules. Can you help with that?
Yeah. Okay. So let me. Okay. So there's a rather important result from I think the 1920s or 1930s by Reitermeister, which is the following statement. So there's a set of, okay, I should be a little bit cautious here, because you're going to run, if you actually try to do this, you're going to run into problems. I usually also give this as a caveat, but I just didn't have time today, that you might think that this and this are equivalent as knots, but they aren't actually, because you really should think the Kauffman invariant is really a ribbon invariant, and you should think of these things as being thickened. If you try to pull this thing straight, it ends up looking like this. So it's actually not a knot invariant of an infinitely thin string. It's a knot invariant of a thickened ribbon. Okay, so this is different from, this is not equal to this. But up to that, Reitermeister showed the following statement, that for knots, he said that, okay, two knots can be turned into each other if, with this move, okay, which we're not going to allow ourselves to do, this move, take two things like this and turn them into this, or this move, where you take a crossing, and I think I drew these before, and then you move this, this behind to above like this. And then similarly, there's one, okay, I think you need another copy of this where the crossing is above the two and it gets moved up. And the base of the statement is any two knots that are equivalent can be converted into each other by a series of just these three moves, okay? These are known as Reidemeister moves. Now, in order to prove that the Kauffman invariant is unchanged, it relates to, is unchanged for any deformation of the knots that you can make without cutting. All you have to do is show that it remains unchanged under Reidemeister moves, okay? So the way you would do it is you would evaluate the Kauffman invariant of these two crossings and show that you would get exactly the same thing that you would get as having them not cross at all, which is basically what I did. I just closed up those way back in this picture. Is basically the same thing. We closed up the top and closed up the bottom to get, instead of just crossing two strands, we actually closed up the top and closed up the bottom, and we related to this, but we could have taken two strands that are not connected in the top and not connected in the bottom and shown that they, it's basically are unchanged under the Reidemeister move, so that, I could take this and close it up and get a circle, and take this and close it up and get that other thing that we drew, okay? So basically, you have to evaluate the Kauffman invariant of this thing and show us the same as the Kauffman invariant of this thing, and similarly evaluate the Kauffman invariant of this and show us the same as the Kauffman invariant of that. So it's not a hard exercise to do, actually. I encourage you to give it a try.
Okay.
Does that answer the question?
Yeah,
Okay.
yeah, I think so.
There's a question from Diptaman.
Hi, Steve. Thanks for a very nice talk.
You're welcome. Good to see you.
So I seem to remember from long ago that there are pairs of knots which are not distinguished by SU21 or any any of the topological quantum field theories. Is that right? Is that correct? Or?
Okay. For any particular, I'm not sure about that statement. I know that the Kauffman invariant does not distinguish all knots from each other, for sure. The simplest two knots, which have the same Kauffman invariant, both have like 16 crossings, so they're pretty complicated. And I don't think I can reproduce them, but it is known that there are some knots that are not distinguished by any Kauffman invariant. I'm not sure if there are any pairs of knots that are not distinguished by any topological quantum field theory. So for example, I think there are pairs of knots that are known that are not distinguished by any Humfly polynomial, which means that no SUN level K can distinguish them. But I don't think that necessarily means that no topological quantum field theory can distinguish them, unless there's a result that I'm not aware of. Okay. Are you aware of this result?
Yeah. No, I think you've answered the question. So basically, okay. SUNK cannot there are pairs of knots which SUNK cannot distinguish.
I'm pretty sure that there are pairs of knots that SUNK cannot distinguish. Okay. But there's a lot of other topological quantum field theories out there.
Okay, thank you.
It's probably actually still a good research question to see which topological quantum field theory can distinguish certain things that are not distinguished by SUNK.
Okay, thank you.
You're welcome.
Okay, any more questions? This might be the time to ask. Okay, there is one question by Abhas.
Yeah.
Abhas, can you unmute yourself?
Yeah. Can you hear me?
Yep.
Yes.
Can you say a bit about the role of gapped spectrum for TQFT to be a valid description?
Yeah, I said that the spectrum should be gapped. And the reason that I want the spectrum to be gapped, TQFT strictly, physically you always want them to be gapped. And the reason that I want them to be gapped is because if it weren't gapped, then there would be lots of low energy particles just flying around everywhere. And that means that I would have a lot of braiding that I didn't have control over. That you would spontaneously create lots of low energy particles and they would braid around everything, and I wouldn't be able to keep a handle on what my what the braid actually is that's being implemented. I don't think there may be a stronger statement about why it is you need a gap, in the sense of that you want certain, to have a well-defined behaved topological quantum field theory, you need certain short scale. I mean, everything is a long length scale description. So it's an effective theory that's applicable at long length scales. If you don't have a gap, if you do have a gap, then that length scale is usually set by some sort of 1 over the gap distance scale, which tells you at what length, at how long a length scale does this thing look like a TQFT. So you need the gap there in order to decide what counts as local and how long a length scale it has to look like a TQFT. If you don't have a gap at all, then you probably have a situation where some correlations are decaying algebraically rather than exponentially, and it may not actually ever look like a TQFT, strictly speaking.
This is the same as saying that, let me say it again, the fact that the geometry is not important, is that also coming from the gap?
Well,
or any
it's not entirely from the gap. I mean, there are plenty of gap systems where geometry is important. Take your usual insulator or something like that. Geometry is important. But the gap is a requirement. It's certainly a requirement.
Okay. Thank you.
You're welcome.
Okay. Any more questions? Okay. If not, I'll thank Steve on behalf of everyone, and thanks, and hope we can have you in ICTS when things normalize.
Sometime soon, hopefully.
Yes. Until then, stay safe, and see you again.
Okay. Bye-bye.
Yeah.
Bye.